Okay, so thank you all for being here. It's been nice chatting with some of you guys in the concourse earlier today. Thank you for the introduction. My name is Rees Pillizzi. I'm a business development representative for the Drones and Geomatics Division of Measure here in BC. And today's presentation will be on the Trinity F90 Plus and Qube 240 LiDAR payload for large area mapping. Quick housekeeping here. We're going to go over an overview of the Trinity, the LiDAR payload itself, some mission planning in the quantum systems Cubase 3D mission planning software. Then we'll move into a quick overview of the processing workflow, cover 3 case studies of the Trinity in the real world, and then a little bit about what comes in the box and overall pricing. First, a little bit about Measure. We are commercial drone and geomatics equipment dealers located here in Burnaby in BC, and then Calgary, Ontario, and Montreal. We have 3 divisions: drones, geomatics, and materials testing. And on the drone division, we carry everything from DJI Enterprise, fixed wing, multispectral LiDAR, cage inspection platforms, pretty much everything robotic we want to be involved with it. In terms of service, we offer repairs and full support for all of our products for their lifetime. Most of us all have a geospatial background, so training is not an issue. And demos. If you would like to see any of these products in person, if you see you have a need, we will come out into the field. We can demo the product for you as well as the software. A little bit about Quantum Systems. So founded in 2015 in Germany, they specialize in eVTOL fixed wing drone platforms. They have over 80 plus employees, and from the ground up have coded their own mission planning and autopilot software. Now, the Trinity F90 Plus. It is a VTOL aircraft, so you can see in the GIF on the right, the props transition, it rises to a set height and transitions back to a plane to execute its mission. This allows you to take off in confined spaces, such as for service roads or dense parks with a lot of tree stands. With the Trinity, there are no belly landings, so it is a VTOL aircraft. It will set itself back down nicely on its landing gear. No tipping on takeoff or landing, meaning it is a very low to the ground platform with the weight centered right around the payload. So on takeoff, it is very stable. You don't have to worry about it potentially tipping off because of the wind. Can take off from the transport case or the ground. We like to take off from the transport case because this allows us to elevate the drone away from any dense vegetation or have you that's there. But when landing, we always recommend landing directly on the ground just to take out any error that might occur if it tips off. And if you so choose, hand catch is possible for those really tight scenarios. Flight time, 90 plus minutes, as is in the name, Trinity F90 Plus. In the field, we see anywhere from 80 to 110 minutes, depending on conditions. So it has the longest flight time of any fixed wing on the market. With the Qube 240 LiDAR payload, because of the added power draw of that LiMAX system, we're going to see a flight time of around 60 minutes. In the bottom left here, we can see some estimated area coverage with the Qube 240. We see 200 plus hectares at 100 meters AGL, pretty standard with LiDAR, with a 50% side overlap. When it comes to RGB mapping, Sony RX1R2 and Sony UMC, anywhere from 170 to 230 hectares flown at 120 meters AGL. And your expected GSD for the Sony is around 1.5 centimeters per pixel, and then 3.19 for the Sony UMC. Tolerance, wind tolerance, 9 meters per second on takeoff. You want to release the Trinity in facing the wind. And then in terms of while it's in cruise mode, it has a tolerance of 12 meters per second, so comparable with the others on the market. Minus 12 to plus 40 degree operating temperature. And we are actually in the process of cold weather testing directly with Quantum and some of our customers up north who have consistently flown this at around minus 20 to minus 25 degrees C. So that should be hopefully approved soon. Trinity is a modular design. This means it can be assembled and disassembled in the field in minutes, and it allows for easy repairs. These parts you see here are all swappable, completely toolless. If you step on a wing in the office, tips off a desk, what have you, you can simply swap out the wing with a new one and you're back up in operation, meaning you don't lose a lot of time in the field. And replacement parts are affordable and readily on hand. Payload capabilities. The long list to my right here. So for RGB mapping, we have the Sony RX1R2, Sony UMC, and then multispectral supports the entire line of MicaSense multispectral payloads, including this year coming the new Red Edge P and Ultim PT. And there are also dual payloads in there as well. So the Red Edge MX you'll see has also a Sony UMC built into that payload bay there. You see he's removing. FLIR Tau 2 coming this year with a Sony UMC. So you're able to get 640 by 512 radiometric data as well as RGB. And of course, the Qube 240 LiDAR payload. And this GIF, it's that easy to swap payloads. It pops out, you pop the new one in, change it in Cubase, and you're ready to keep flying. Included in the box is the iBase GNSS base station. This is a standard option that comes with all Trinities. It is a GNSS base station that can be used to PPK process all your data. This is a PPK platform. It tracks L1, L2, L5 signals, and GPS, GLONASS, Beidou constellations. You're able to get 10 hours on a single charge. If you bring a portable battery into the field, you're able to extend that life pretty much indefinitely. And so our best practice is to place this on a known survey pin or monument to obtain the best accuracy, but it is PAP workflow supported, so you can run it through Enercam PPP to get your corrected base station coordinates and use that for processing. Also important to note, Trinity, all its payloads, including the Qube, support PPK through other third-party base stations. So if you're already familiar with StoneX, Leica, TopCon, what have you, those will all be able to be used for processing. So quick comparisons here. Anything in blue is something that we see either matches a competitor or is also or something that Trinity excels in. VTOL, yes, it is a VTOL aircraft, as is the next, and unlike the other one where it requires a belly landing. Flight time, 90+ minutes, 60 minutes with the Qube, and based on the list, just the longest and most flexible amount of sensor capabilities. It is modular. Included in the box is a physical RC controller. Others do have a tablet or no controller whatsoever. It's an option. Some like to have, like myself, like to have actual, tactile feedback while flying for emergency purposes. This isn't a fully autonomous drone, but you can take over control at any time. It does support PPK, as is standard in all packages. It has ADS-B in included as standard, and ADS-B out is also an option. Base station, again, the iBase is included in every box with no added charge, and it is third-party base station compatible. Onto the Qube 240 LiDAR. So Quantum Systems partnered with Yellowscan LiDAR. They have an exclusive relationship to essentially build a LiDAR package payload for the Trinity F90+. This is the first on the market right now for fixed-wing VTOL drones. And essentially, it is a Yellowscan Mapper Plus that they have essentially stripped down to fit in a Trinity payload bay, made necessary modifications for ventilation, and fully integrate the entire, everything that's important in that Mapper Plus. So the Planix INS system, the LiveVox sensor, and antenna. So why LiDAR? So a lot of you are familiar with this technology already, but a quick overview for those that aren't. It's a remote sensing technology that basically uses a pulse laser for measurements. This allows you to achieve high vertical accuracy in areas with a lot of dense vegetation and achieve accurate terrain models in those areas as well. It can be flown on sites with poor visibility, and on paper, you can technically fly LiDAR at night because it's a laser system, you're gonna get good data. You can capture details in small diameter, so that's one thing we run into, an issue with photogrammetry where power lines, say, don't necessarily show up in your point cloud, LiDAR is gonna take care of that. And a little bit faster processing time, and you can map nonlinear areas due to the FOV. Fixed wing versus multi, we get asked this quite a bit. Quick few points. Essentially, it boils down to area coverage. If you have a large area to map, it makes more sense to use a fixed wing instead of planning multiple flights with a multi-rotor. Straighter flight lines, because the drone has to bank and come back in to align itself up, you ultimately end up with a little bit smoother data. And because of these banks, with a LiDAR system specifically, it keeps the IMU initialized by offering constant momentum during the flight. Doesn't, like a traditional multi-rotor, stop, turn, go to the next flight line and continue. And because there's no gimbal mounts, it is a fixed state system. Your lever arms measurements for post-processing are a fixed value, which makes things a little bit easier on the back end. Specs, so it is the LiveVox Avia sensor that I'm sure a lot of you have seen before. It has a 70.4 degree FOV capable of 240,000 shots per second with 3 echoes, and it's been integrated with an Planix APX-15 INS system. The Planix is a Trimble company. If any of you are familiar with on the geospatial end, Trimble is a reputable brand, so we are able to achieve very accurate georeference data. These are the typical numbers we see in ideal conditions, around 2 centimeters precision and 3 centimeters accuracy. So why the LiveVox Avia? Because it's not a spinning puck, it is a fixed state sensor. We're able to fly a little bit faster and a little bit lower and still get good point density. Planix APX-15 INS has an IMU precision of 0.025 degrees, and our recommended flight parameters here are around 50% side overlap at 100 meters AGL. Pretty standard practice for our pass-borne LiDAR. So quick overview of the point density by ground speed and altitude. With its FOV of 70.4 degrees, we can see here the blue line, 17 meters a second is around where the Trinity will be flying on the bottom line. So at 100 meters AGL, we're gonna see a point density of around 100 points per square meter, if not a little higher. We have seen several hundred points per square meter, depending on vegetation, and a little bit less, but you can always resample these later to make processing a little bit easier. It is important to note, we do say be careful of the headwind or tailwind. We always plan the Trinity to fly crosswind, as tailwind and headwind will slow down and the drone's triggers, and can lead to either lapses in the data for point density with LiDAR, and then for photogrammetry, you could miss triggers and be missing images altogether. And of course, vegetation, slope, reflectivity, that affects all of this. One button operation, yellow scan, because this is a yellow scan system, prides themselves on their motto, just press the yellow button, which means in order to start data capture, once the IMU is warmed up and initialized, you simply press the button and it starts scanning. Same way when you complete your mission, when the drone lands, tap the button again, stops data recording, and you are ready to begin processing in the field. And I will get to that software shortly here. Quick workflow. So you're going to flight plan in Cubase 3D, which is the autopilot software. You can import your own custom DEMs. We'll get to that. 3D view, camel import, etc. Data capture, the one button operation with the Trinity's flight, and all the data stored on a 128 gig USB stick. Post-processing, you'll use a Planix POSPAC UAV to geotag your images, and then also Cloud Station Core to actually do your strip adjustment, colorization, and all your actual point cloud editing. And then output, you can output an LAS, LAZ, DTM, DSM, DHM Hillshade model, and then in any coordinate system, so NAT83 CSRS, and Cloud Station does support custom coordinate systems if that is involved in your workflow. Cubase 3D. So we can see a quick 3D view of what this flight plan actually looks like. It's Windows 10 and it is free. It's included with every Trinity, and there's an unlimited number of seats on this software. So if you have multiple pilots running multiple laptops, it is completely free for them to also download this at any time. It's used for flight planning and geotagging, not for the Qube though. That is done in a Planix PostPac, but all your other payloads is done in Cubase. Can supports area and corridor mapping, 3D view, and then you can also do custom paths for specific jobs. So we can kind of see here on the right-hand side, a quick GIF of what it looks like as you edit your paths. You can download elevation data. This is all built into Cubase, but for those areas that are either large earthwork sites, mine sites, what have you, you can import your own DEM in the form of a TIFF in WGS 84. And this is especially useful for those really, in Northern Canada where this public data is not readily available nor accurate, and you do want to fly with an accurate DEM for the best terrain following, translating into better accuracy. This is an example of that. One of our friends up in Qualuit, in Nunavut, this is the DEM he used for a project not too long ago. That is actually covered in the case study, but this is his custom DEM he imported and used for all of his Trinity flights. Area planning, simply click and draw like any other mission planning software. If you're familiar with DJI Pilot, what have you. You set your entry and exit extensions. You can optimize the leg path. Usually we want to start the Trinity. Its first waypoint should be the furthest point from you, so that way it works its way back to you. And if anything happens, it's not a kilometer down the way that you got to go retrieve it. And we can see that kind of being edited on the right-hand side here. You will also be editing your payload. You can set your overlap, as well as any other flight parameters you'd like to include. So when it comes to LiDAR, as I'm sure some of you are familiar, LiDAR, you need to fly calibration loops to initialize that IMU. So with any like this, all you have to do is click Add LiDAR Calibration Loop. The Trinity will basically take off in one direction, come back. It needs that acceleration to activate the IMU, and then execute its mission. And it will do this automatically at the beginning and end of its data capture. Terrain following, there are several different options here on the left. Above max area, pretty explanatory. Cross legs, it's going to fly in a crosshatch pattern, which yields a ton of data, so it's not necessarily recommended, but it is an option. Above average leg, it's going to average out to max altitude, or average out the leg altitude and fly at a constant height. Above max leg, it's going to pick the highest point per flight line and fly at a constant altitude above that. And then of course, advanced terrain following, which essentially on the bottom of the screen here, you can kind of see what that DEM looks like. It will add many waypoints to make sure that the Trinity makes corrections in the air as needed to contour with the Earth. On the left, we see a Cubase mission plan pre-flight, and on the right is the recorded trajectory from the LiDAR unit in a Planix post-spec. So this is your corrected trajectory, and we can see just how closely and accurately that mirrors it. ETOL aircraft, so here we see the Trinity taking off. It is going to transition right here and then go out to execute its mission. You'll notice the pilot was completely hands-off on the RC. It is fully autonomous. In Cubase, you have live monitoring of all aspects of the aircraft. You can see it executing its mission in real time. On the top right where that mouse is, the little camera icon, you can actually see that number climbing as it in real time shows how many times that camera has triggered. And then you, of course, have your telemetry data between the RC, the aircraft, your modem, and then battery life. Very useful tool. And again, comes in on landing, so it will transition to a set altitude that you pre-plan. The Trinity will then set itself down right where it landed. So in this, we will see just how close it finishes based on where it actually took off. And that was, the pilot did have the RC control in his hands for safety purposes, but the drone will do that by itself. He did not need to make any adjustments because it was a relatively calm day. At the end of your mission with the Qube 240, you'll end up with 3 files. You will have the your LVX file, which is your raw LiDAR data, .to4, and a .apx file. With these files, your file import, you're going to take your APX and all your decimated trajectory data and import that into a Planix post-back UAV. This is your first stop on processing. Then you're going to set your corrected base location, whether it's a known pin or you PPP that data. GNSS inertial processor 1, verify your lever arms measurements, which is very easy given it is a fixed measurement. It's not on a gimbal. Set your export settings, run it through another processor, export that SPET, and you're off to the races, and you can move over to Cloud Station Core, where you will extract your points from your flight lines and get rid of any outliers, any overspray from the LiDAR sensor. Anytime the aircraft was turning, we don't like that data. Apply your strip adjustment, which will algorithmically align your flight lines and your point cloud to obtain the best accuracy possible. Terrain classification, ground versus non-ground points to export your DEM, and then ultimately export your DTM, DSM, Hillshade, what have you, in LAS or LAZ 1.2 and 1.4 file formats. Again, there's that again. On the left-hand side here, we see what the raw point cloud after processing looks like in Cloud Station, and on the right, we see a exported model. First case study. So Saskatchewan Polytechnic, it's a bit of a wordy slide. I know my undergrad, I hated these, but bear with me. Basically, they acquired a Trinity F90 Plus and a Qube 240 LiDAR to detect small changes in elevation at high resolutions. Their research principle was to study how current farming practices can be used to optimize water and fertilizer efficiency across treatments in sandy soils. And then by determining the drainage runoff of these sites was an important factor for that sail type. Here's a mission plan. You've seen actually this Cubase mission plan before on the left. The LiDAR flight took 12 minutes and 30 seconds. They covered 22 hectares. Battery burn was 21%, and their side overlap was 50. On the right-hand side, they flew a second flight to colorize their point cloud. Now, there is not a dual payload available yet. That is in the works for the Qube 240, which will be able to capture simultaneous RGB and LiDAR data for an automatically colorized point cloud. But for now, it needs to be flown in a separate flight. Here, they use the Sony RX-1R2. Again, 22 hectares, 21% battery burn, and 18 minutes with a 75-75 overlap, sorry. And here's the total area covered, 61 hectares. This was completed in a day, and much of this was not in their AO, but you can see some overspray and it still has that accuracy. Again, so that colorized version of their flight, which is their actual area of interest, is right here. And on the next slide, we'll see a zoomed in version where you can see the detail that was provided by that Sony RX-1R2 to the point cloud. Pretty impressive data set. LiDAR survey in the high Arctic. So our friends at Arctic UAV employed the Trinity F90 Plus with the Qube 240 LiDAR to essentially map out different, or look at different road options for access to a very remote lake. This was very hard to do as they had to battle constantly changing and unpredictable conditions with winds ranging from 5 meters a second to 12 meters a second. And they had to helicopter into all of their home locations. A little blurb from Kurt here, who's the CEO. The project saved their customer over $100,000 over traditional helicopter and external LiDAR systems. The Trinity and the Qube 240 is a great addition to our fleet, great project, and success for all involved. Here we see the helicopter loading up their equipment in a sling. They're going to long line that in. And this, again, it was a really remote AO. They had a helicopter in, and what they did is they essentially leapfrogged that helicopter every 3 to 4 kilometers with the Trinity in the case and all their other gear to their each set takeoff locations. The nice thing is that Trinity, it is a large aircraft if you have seen it on the table. However, it does pack down into a 3.5 foot by 3.5 foot padded case. So putting it in a helicopter in a sling like this is not a problem at all, or the back of a truck. Here is the data. In total, they covered 750 hectares. They did 21 total flights, and 10 of those were at the Qube 240. The other 11 were for either photogrammetry or for colorization of that LiDAR data. All done visual line of sight, 30 to 40 minutes per flight. And again, as I mentioned, they traveled by helicopter every 3 to 4 kilometers. And they did this in just over a week. Impressive in that remote area. Last one, Rocket Mine. Quantum was tasked with mapping 6,500 hectares of area in dense tropical canopy just for a mitigation plan. As you see here, there's a sedimentation basin. That is, they were mapping the entire flood basin in case of a dam breach. Here's their mission plan, 20 flights, 100 to 120 meters AGL, 6 takeoff locations, 5 flights per day. This was all completed in just 4 days, all 6,500 hectares. On the next slide, we'll see their mission plan, day 1, day 2, day 3, and those 6 different home points and a picture of the Trinity. And again, this is very dense tropical canopy. So thankfully, the Live Oxavia does have 3 returns to be able to actually make contact with ground and get you good data. Here's the raw point cloud, and these are the raw ground points. We can see the accuracy it captured within the canopy as well as the points on the ground. Elevation checks, they shot these with traditional survey methods to check their data. And on the bottom right, we can see here, their mean accuracy was around 2.3 centimeters. Final results, 19.3 hours of flight time, over 11.1 billion points were captured. 2.6 billion of those were on the ground. About 40 points per square inch. They then resampled this to 4 points just to ease on processing. And here we see the bottom, we have their DTM bottom left, and on the right, their 50 centimeter contour lines. And this was all used to build their risk assessment. 4 days in the field. Finally, in the box for 26.5, it includes the base space station, as I mentioned, an RC, and everything you need to be operational, including a battery and charger. Optional extras are, extra parts, if so, what have you, but this is all for that price, including a GNSS base station, which is typically not the standard. And then the Qube 240 Trimble AV14 GNSS antenna, which mounts to the top of the Trinity, and then flash drives, USBs, microfiber cloth, Pelican case for carrying, security, what have you. And it does include an annual subscription to Cloud Station Core, which is Yellowscan's software, and then the strip adjustment module, which is a nice inclusion as it cuts down on your software costs in getting into the system. All right, I had to burn through the last few slides there, but thank you so much for being here. I hope you guys learned anything. And if you have any questions about this system or any other drone payloads, you can email contact@measure.ca or come talk to me out front. We'll be there for the next couple hours. Thank you guys again, and I look forward to meeting more of you as time goes along here. Thank you.
Questions? Anybody? I think.
How did you keep the line of sight on your drone in that thick, dense tropical canopy?
So the Rocket Mine case study? Yeah, that was quite difficult, but they essentially they tried to set their takeoff points at a little bit of a higher elevation, so they could kind of have a look down at the site. The topography was that enough where that afforded them the ability to do so. Definitely tricky though.
We've got a question up here.
We actually bought a Mika Sense from you guys. Can you mount that in the Trinity, or do you have to get a specific? Because I'm thinking of doing the, with the Trinity, doing multi-spec. Mm-hmm. Do you have to get is it a specific payload, or can you take the Mika Sense camera and mount that in the bay of the Trinity?
It is a specific payload, but you can essentially get a custom integration kit from a Quantum, and then we can integrate that. Well, it's Mika Sense Ultim, PT, or one of the...
No, it's the Red Edge MX.
Okay, yep, that can be integrated into a payload bay, and as well, the Trinity also supports the DLS2 light mount on that top part. So it's just a matter, and the cable to connect that is integrated into the actual board of the aircraft, so there's no need to run out extra wires.
Cool, thanks.
Yep, you're welcome.